Every atom in your body is almost empty space. If you were to remove that emptiness, compressing only what we once believed was solid, the entire human population could fit inside a sugar cube. This is not poetry, it is not a metaphor, it is a measured consequence of physics. And yet for centuries, we were utterly convinced that matter was solid, indivisible, and real in the most ordinary sense of the word. We trusted our eyes. We trusted our hands. We trusted the ancient instinct that tells us a table is solid because it resists us, that a stone is real because it hurts when it strikes, that the world is made of little things bumping into other little things in an otherwise empty void. That intuition shaped not only our science, but our philosophy, our language, and even our sense of identity. We are taught from childhood that the universe is made of objects, stable, local, persistent, things that exist whether we look at them or not. This belief did not arise from ignorance, it arose from success. Classical physics, crowned by Isaac Newton in the 17th century, was so powerful that it bordered on the miraculous. With a handful of equations, humanity learned to predict the motion of planets, the fall of apples, the swing of pendulums, and the rise and collapse of tides. The universe appeared as a vast mechanical clock, ticking forward with perfect precision. Every object had a position, every object had a velocity, and given enough information, the future itself seemed calculable. In this world, particles were the foundation of everything. They were idealized as point masses, objects with no size, no internal structure, but with definite locations and trajectories. They moved through absolute space, governed by deterministic laws. At any given moment, each particle was somewhere, doing something, whether or not anyone was watching. This vision of reality felt not only mathematically elegant, but psychologically satisfying. It matched human intuition. It mirrored how we survive. Our brains evolved to track solid objects moving through space, to predict collisions, to identify threats and tools. A universe built from particles made sense because we were built to believe in particles. Determinism followed naturally. If the universe is a machine, then the future is simply the past unfolding. There is no ambiguity at the fundamental level, only ignorance. As Pierre-Simon Laplace famously imagined, an intellect that knew the position and momentum of every particle could calculate the entire history of the cosmos, forward and backwards, without uncertainty. Chance had no place in reality itself. It existed only in human error. Locality was just as sacred. Objects influenced one another only through direct contact or through forces that propagated across space. Nothing happened instantly at a distance. Nothing acted mysteriously from afar. The universe respected boundaries and object permanence. The idea that things continue to exist even when unobserved was not merely assumed, it was unquestioned. To doubt it would have seemed pathological. This was not just physics, it was a worldview. For more than 2 centuries it worked. Cannonballs obeyed it, steam engines obeyed it, bridges stood because of it. Empires were built upon calculations that assumed matter was solid and predictable. Even when atoms were proposed, they were imagined as tiny versions of familiar things, miniature billiard balls colliding in the dark. But beneath this triumphant success, something subtle was already beginning to crack. The first warning signs did not come from wild speculation or philosophical doubt. They came from precision, from experiments that worked too well, from measurements that refused to align with expectations by margins too small to ignore. Light, long understood as a wave, began behaving in ways no wave should. Energy arrived in discrete packets. Heat refused to distribute itself smoothly. Radiation from hot objects deviated from classical predictions in ways that could not be patched with better math or finer instruments. Then came the atom itself. Atoms were not behaving like miniature solar systems, despite every effort to force them into that picture. Electrons, if treated as classical particles, should spiral into atomic nuclei and annihilate matter in a fraction of a second. They did not. Something was holding them in place. Not a force in the Newtonian sense, but a rule that had no classical explanation. At smaller scales, certainty began to blur. Trajectories lost meaning, predictability frayed. The very concepts that once defined reality, position, motion, solidity, became strangely difficult to apply. And yet, the greatest obstacle was not technical, it was psychological. We were trapped by a picture that had worked too well for too long. The idea of particles felt obvious, not because it was true, but because it was useful, because it aligned with our senses, because it allowed us to imagine reality as something graspable, countable, and composed of parts. To question particles was to question whether the world itself was made of things at all. And that is the discomfort we will sit with. In this journey, we will trace how the most successful idea in the history of science, the solid particle, began to dissolve under scrutiny. We will see how determinism gave way to probability, how locality was challenged, and how object permanence itself came under suspicion. We will follow the slow, reluctant realization that the universe might not be built from objects moving through space, but from something far stranger and less intuitive. This is not a story about mistakes. Newton was not wrong in the way superstition is wrong. Classical mechanics remains astonishingly accurate within its domain. The planets still obey it. Bridges still stand because of it. But truth in science is not a throne. It is a boundary. And beyond that boundary, the familiar shapes of reality begin to lose their edges. As we proceed, we will ask questions that physics itself cannot yet answer cleanly. Are particles fundamental, or are they emergent appearances? Is matter made of things, or of relationships? Is the solidity we experience a deep feature of reality, or a convenient fiction written by our senses? If you find yourself unsettled by these questions, that is not a failure of understanding. It is a sign that you are approaching the edge of what intuition can safely carry. And if this exploration resonates with you, if you feel that quiet pull of curiosity that refuses easy answers, you may wish to stay with us as this journey continues. Because what begins here, with the crumbling of the solid world, will soon lead us to a place where even the word particle starts to sound like an echo from a reality that never truly existed. Light was supposed to be simple. For centuries it seemed obedient, predictable, almost courteous. It illuminated objects without altering them, revealed the world without disturbing it. We could trace its paths with mirrors, bend it with lenses, trap it in glass. To the human mind, light appeared to behave like a stream of tiny messengers racing across space, each one carrying information from one place to another. That picture felt natural. It felt correct. Isaac Newton certainly thought so. To Newton, light was made of particles. He called them corpuscles, small, discrete entities emitted by luminous bodies and traveling in straight lines. Reflection and refraction were explained as mechanical interactions between these corpuscles and matter. The theory fit the era's intuition perfectly. If the universe was built from particles, then light too must be particulate. After all, shadows had sharp edges. Light traveled in straight lines. It bounced. It behaved, at least superficially, like a stream of tiny objects. But even as Newton's authority solidified this picture, a rival idea quietly refused to disappear. Christian Huygens proposed something radically different. Light as a wave, not a collection of objects, but a disturbance spreading through space, much like ripples across water. Each point on a wavefront, he argued, becomes the source of new wavelets. Reflection and refraction were not collisions, but the bending of a continuous phenomenon. For decades, this wave view struggled for acceptance. Waves, after all, were known to require a medium. Sound needed air. Water waves needed water. If light was a wave, what was waving? No one could identify the medium. And so the particle view endured, buoyed by Newton's prestige and by the human preference for tangible things. Then came an experiment so simple and so devastating that it would quietly undo the certainty of particles without shouting its intentions. In 1801, Thomas Young passed light through two narrow slits and projected it onto a screen. If light were made of particles, one would expect two bright regions corresponding to the two slits. Instead, what appeared was a pattern of alternating bright and dark bands, interference fringes. Light waves overlapped, reinforcing each other in some places and cancelling out in others. Particles cannot cancel themselves out. Waves can. This was not a philosophical argument. It was not speculation. It was geometry painted in light. The universe had, without explanation or apology, drawn a wave equation onto a wall. Diffraction experiments soon followed. Light bent around edges, spread through narrow apertures, behaved in ways utterly foreign to classical particles. One could still speak of rays for convenience, but beneath that approximation lurked something continuous, something extended, something fundamentally unparticle-like. The victory of the wave picture seemed complete. Then, physics did something unexpected. It went deeper. In the mid-19th century, James Clerk Maxwell unified electricity and magnetism into a single mathematical framework. From his equations emerged a revelation. Light was not merely a wave, it was an electromagnetic wave. Oscillating electric and magnetic fields propagated through space at a fixed speed. No particles required, no mechanical pushes, just fields evolving according to precise laws. For the first time, light was not an object moving through space. It was space itself doing something. This was revolutionary in a way that is easy to underestimate. Fields were not things in the traditional sense. They did not have edges. They did not have trajectories. They existed everywhere, even where nothing else seemed to be. A field assigned a value to every point in space and time, whether or not anything occupied that point. And light, according to Maxwell, was a self-sustaining dance of fields. The particle picture was not merely challenged, it was sidelined. By the late 19th century, most physicists believed the matter was settled. Light was a wave. The universe was continuous at its foundations. Particles belonged to matter, fields belonged to forces. The story seemed tidy, it did not last. At the turn of the 20th century, a quiet crisis emerged from the study of heat. When physicists calculated how hot objects should radiate energy, classical wave theory produced a catastrophic prediction: infinite energy emitted at high frequencies. The so-called ultraviolet catastrophe was not a small discrepancy. It was a complete collapse of the theory. The fix came from an uncomfortable idea. Energy, it seemed, was not emitted continuously. It arrived in discrete packets. Max Planck introduced this quantization reluctantly, treating it as a mathematical trick rather than a statement about reality. But the damage was done. Then Albert Einstein took the idea seriously. In explaining the photoelectric effect, Einstein proposed that light interacts with matter not as a continuous wave, but as localized packets of energy. Later called photons, these packets struck electrons like particles, ejecting them from metal surfaces only if the light's frequency was high enough, regardless of intensity. More light did not help. Brighter light with insufficient frequency did nothing. Dim light of the right frequency worked instantly. This behavior made no sense if light were merely a wave, but it made perfect sense if light arrived in discrete interactions. And so the crisis emerged in full view. Light interferes like a wave, yet arrives like a particle. This was not a failure of experimental resolution. It was not a missing variable. It was a direct contradiction of classical categories. Light refused to choose. Physicists were forced into a deeply unsettling position. The same entity exhibited mutually exclusive behaviors depending on how it was observed. In some experiments, light spread out, overlapped with itself, and cancelled itself out. In others, it appeared to strike detectors in localized, indivisible events. Neither picture could be discarded. Both were necessary. Neither was sufficient. And lurking beneath this contradiction was a more dangerous implication. If light, the most well-understood phenomenon in classical physics, could not be described as either a particle or a wave, then perhaps these concepts were not descriptions of reality at all. Perhaps they were tools, approximations, shadows cast by something deeper that did not resemble either category. Fields began to look less like mathematical conveniences and more like fundamental entities. Unlike particles, fields could exist everywhere at once. They could interfere, they could store energy, they could give rise to localized effects without being localized themselves. The universe, it seemed, might not be built from objects moving through space, but from continuous structures filling space entirely. Yet even fields did not resolve the paradox. The packet-like arrival of light refused to disappear. The photon was not a return to classical particles. It was something new, an interaction event, a quantized exchange, a rule governing how fields talk to matter. By the early 20th century, physics stood in an uncomfortable place. Light was neither wave nor particle, yet displayed the traits of both. Classical intuition had fractured. The old certainty that reality was made of things was beginning to erode. This was not merely a technical inconvenience, it was a warning. If light, the messenger that reveals all other things, could not itself be cleanly described, then perhaps the fault lay not in light, but in the categories we used to think with. Perhaps the universe was not obligated to conform to the shapes our minds preferred. And if that were true, then matter itself, the very particles we believe ourselves to be made of, might soon face the same reckoning. If you sense that something foundational has already slipped out of place, you are right. And if you feel the urge to follow where this disturbance leads, to see whether matter can survive the same scrutiny that light has just endured, then it may be worth staying with this journey. Because what light has just done is not an exception, it is a preview. At the end of the 19th century, physics believed it was nearly finished. The laws governing motion were known. Electricity and magnetism had been unified. Light had revealed itself as a wave propagating through fields. Many leading scientists assumed that all that remained were minor refinements, small corrections to be filled in by careful measurement. Then the universe delivered a shock. It came not from the distant stars or the deepest atoms, but from something deceptively ordinary: heat. When objects are warmed, they glow. Iron turns red, then white. Stars shine because of their temperature. This glow, known as thermal or blackbody radiation, should have been straightforward to explain using the well-established wave theory of light. It was not. Classical physics made a clear prediction. A heated object treated as a collection of oscillating charges should emit radiation across all frequencies, with energy increasing without bound at shorter wavelengths. The mathematics was unambiguous, and it was catastrophically wrong. According to classical theory, any warm object should release an infinite amount of energy in the ultraviolet. The universe, if described by those equations, would have burned itself apart instantly. This failure became known as the ultraviolet catastrophe, not because it was dramatic in practice, but because it was theoretically fatal. Experiments were precise. Measurements were consistent. The flaw lay not in the data, but in the assumptions. Something fundamental about energy itself was being misunderstood. In 1900, Max Planck attempted what he believed was a temporary fix. Desperate to match theory with observation, he proposed that energy could not be exchanged continuously, but only in discrete amounts. These packets of energy were proportional to the frequency of the radiation. Higher frequency meant larger packets, lower frequency meant smaller ones. Planck did not believe this described reality. He regarded it as a mathematical convenience, a trick to force equations into alignment with experiment. The idea offended classical sensibilities. Nature, after all, was supposed to be smooth, continuous, infinitely divisible. But the equations worked. For the first time, energy itself appeared to have a smallest unit. It did not flow freely like water. It arrived in steps. This was not merely a correction. It was a rupture. 5 years later, Albert Einstein took the rupture seriously. In studying the photoelectric effect, the emission of electrons from metal surfaces exposed to light, Einstein encountered a result that could not be explained by waves alone. Classical theory predicted that increasing the intensity of light should eventually eject electrons, regardless of color. Experiments showed otherwise. No electrons were emitted below a certain frequency, no matter how bright the light. Above that threshold, electrons were emitted instantly, even at low intensity. Brighter light increased the number of electrons, not their energy. This behavior was impossible to reconcile with a continuous wave delivering energy gradually. Einstein proposed a radical solution. Light interacts with matter in discrete energy packets. Each packet carries a fixed amount of energy tied to its frequency. An electron is ejected only if a single packet provides enough energy in one interaction. Light in these interactions behaved as though it were made of localized quanta. Einstein did not claim that light was a classical particle. He did not imagine tiny balls flying through space. What he proposed was subtler and more disturbing. The electromagnetic field, though continuous in its propagation, exchanged energy in discrete events. The interaction itself was quantized. This distinction matters. Particles, in the classical sense, are objects that persist through time. They have trajectories. They occupy positions. What Einstein introduced was not an object, but an event, a transfer, a unit of interaction. Light had re-entered the particle conversation, but transformed. This was the quantum shock. Energy, long treated as a smooth quantity, revealed itself to be granular at its most fundamental level. The universe did not permit arbitrarily small exchanges. Nature enforced minimums, and once that door was opened, it refused to close. If light could only give and take energy in discrete amounts, then the smoothness of classical physics was an illusion born of scale. The apparent continuity of the world was an average effect, emerging only when countless quantum events blurred together. What appeared fluid was, at its core, stepped. This revelation carried a deeper implication. The mathematics describing fields, those continuous structures filling space, remained intact. Maxwell's equations still worked, light still interfered, waves still spread. Yet when it came time to interact, to exchange energy with matter, something abrupt happened. The universe behaved like a system that evolves smoothly but communicates discreetly. This was not a compromise between wave and particle. It was something entirely new. The quantum of energy was not a thing moving through space. It had no definite position until it interacted. It was defined by what it did, not by where it was. The old particle picture, solid, localized, persistent, no longer applies. Physics had stumbled upon a world where processes mattered more than objects. At first, the implications were narrowly contained. Planck and Einstein were addressing specific experimental puzzles. But the logic could not be confined. If energy itself were quantized, then atoms could no longer be miniature classical systems. Their stability, their spectra, and their behavior would need new rules. The quantum shock reverberated outward. Spectral lines appeared at precise frequencies. Atoms absorbed and emitted energy only in fixed jumps. Chemical behavior became a matter of allowed transitions rather than continuous change. The idea of smooth motion within atoms began to collapse. What was emerging was a universe governed not by trajectories, but by transitions, not by continuous flows, but by permitted steps. And with this shift came a quiet but profound redefinition of what it meant to be real. In classical physics, reality was a state, positions and velocities at a given moment. In the quantum view, reality began to look more like an event, an interaction, a measurement, an exchange. The fundamental units of nature were no longer objects occupying space, but occurrences connecting systems. Light, once the epitome of continuity, had forced this realization into the open. The shock was not that particles existed again, it was that the particle concept itself had changed. What returned was not solidity, but discreteness. Not objects, but quanta. The old certainty that the universe was made of little things moving through space was now visibly strained. Something deeper was at work, something that refused to be pictured as either a wave or a particle in the classical sense. And if light, the most thoroughly studied phenomenon in physics, behaved this way, then it was only a matter of time before matter itself would be dragged into the same unsettling light. If light could behave like matter, then the question that haunted physics next was unavoidable. It was not poetic, it was not philosophical, it was brutally logical. Could matter behave like light? For centuries, matter had been the last refuge of solidity. Stones fell, metals bent, dust scattered. Whatever uncertainties surrounded light, matter still seemed anchored to common sense. It had weight, it had location, it endured. Even when atoms were accepted, they were imagined as tiny, indivisible pellets, reliable carriers of mass and momentum. To suggest that matter itself might possess a wave nature was to threaten the final boundary between intuition and abstraction. And yet, in 1924, a young French physicist named Louis de Broglie made exactly that suggestion. His reasoning was disarmingly simple. Light, once thought to be a wave, had revealed particle-like behavior through quantized interactions. If nature was willing to blur that distinction in one direction, why not the other? Why should waves alone enjoy duality? Why should matter be exempt? De Broglie proposed that every particle with momentum should be associated with a wavelength, not metaphorically, not approximately, literally. The wavelength, he suggested, was inversely proportional to the particle's momentum. Large objects with enormous momentum would have wavelengths so tiny they were effectively undetectable. But electrons, atoms, and subatomic entities might exhibit wave behavior under the right conditions. This idea was not derived from experiment. It emerged from symmetry, from a sense that nature, once it breaks a rule, rarely breaks it halfway. At first, the proposal seemed implausible. Matter waves could not be seen. They did not ripple water. They did not diffract around doorways. Everyday experience offered no hint that a baseball carried a wavelength. The concept felt artificial, an elegant mathematical flourish untethered from reality. But physics had learned by then to distrust comfort. Only 3 years later, in 1927, the question was settled, not by argument but by observation. Clinton Davison and Lester Germer were studying how electrons scattered off a crystalline nickel surface. Their goal was not to test de Broglie's hypothesis. In fact, the experiment began as a calibration exercise, complicated by an accidental overheating of their apparatus. When they examined the scattered electrons, they noticed something unexpected. The electrons did not scatter randomly, as classical particles should. Instead, they formed a pattern. Sharp peaks appeared at specific angles, precisely matching the interference pattern predicted for waves reflecting off a regular lattice. Not light waves, matter waves. The measured angles corresponded exactly to de Broglie's predicted wavelength for electrons at that energy. No adjustments were required, no additional assumptions. The numbers aligned with unsettling precision. Electrons, entities long treated as point-like particles, were diffracting. This was not an interpretation layered onto ambiguous data. It was geometry again. Interference drawn in electron counts, the same mathematics that governed light waves now governed matter. Within months, similar experiments confirmed the effect. Electron diffraction became a standard tool. Later, neutron diffraction, atom interferometry, and even molecule interference extended the phenomenon to increasingly complex systems. Matter waves were not hypothetical, they were measurable, and with that, the classical distinction between matter and radiation collapsed. The electron, once imagined as a tiny charged object tracing a definite path through space, now exhibited behavior that no particle should possess. It spread, it overlapped with itself, it interfered, it explored multiple paths simultaneously, not as a metaphor, but as an experimentally verified necessity. Attempts to salvage classical intuition only deepened the mystery. If the electron was truly a particle, through which slit did it pass? The interference pattern demanded that it pass through both, or through neither in any classical sense. The electron did not behave like a localized object moving from point A to point B. It behaved like a distributed phenomenon whose effects became localized only upon interaction. And this localization did not reveal a hidden trajectory. It ended the wave-like behavior entirely. What de Broglie had uncovered was not a duality between two separate modes of existence. It was a failure of the categories themselves. Matter was no longer something that merely occupied space. It was something that evolved across possibilities. The implications were profound and deeply uncomfortable. If electrons possessed wavelengths, then the stability of atoms could no longer be explained by particles orbiting nuclei like planets. Orbits implied paths. Paths implied positions. Positions implied continuous motion. But matter waves do not orbit. They form standing patterns. They occupy allowed configurations determined by boundary conditions, not by force balances alone. The atom became less like a solar system and more like a resonant structure, a system of permitted modes. Matter, it turned out, does not move through atoms. It arranges itself. This shift marked a quiet revolution in how reality itself was described. The fundamental entity was no longer the particle's position, but its wave function, a mathematical object encoding all possible outcomes. The particle was not somewhere until it interacted. Between interactions, the notion of location lost its meaning. Yet this wave nature did not behave like classical waves either. Matter waves did not carry energy in the familiar sense. They did not dissipate. They did not exist as vibrations of a material medium. They were probability amplitudes, structures that governed the likelihood of events. The electron wave was not a substance. It was a rule, and that rule was non-negotiable. The success of electron diffraction destroyed the final refuge of classical realism. One could no longer argue that waves belonged to light, while particles belonged to matter. Nature did not respect that division. The universe did not sort its entities according to human expectation. What had once been thought of as the building blocks of reality were now better understood as manifestations of deeper principles. The electron was not a thing with wave-like behavior added on, nor was it a wave pretending to be a thing. It was something that demanded a new language entirely. Even more unsettling was the scale of the effect. Matter waves were not confined to exotic laboratory conditions. They were present everywhere, in every atom, in every chemical bond, in every piece of solid matter. The solidity we experience, the rigidity of tables, the resistance of walls, is not the result of tiny particles pushing against each other like grains of sand. It arises from wave patterns constrained by quantum rules, enforced by the geometry of allowed states. The world feels solid, not because it is made of hard things, but because certain configurations are forbidden. This realization marked a turning point. Light had first hinted that classical categories were unreliable. The quantum shock had revealed discreteness beneath continuity. Now matter itself had crossed the line. Particles were no longer privileged occupants of reality. They were no longer the unquestioned foundation. They had become secondary, effects emerging from something more abstract, more distributed, and far less intuitive. The universe, it seemed, was not built from objects moving through space, but from patterns of possibility constrained by mathematical law. And if matter itself could interfere, then the very idea of a particle as a persistent, localized thing was no longer a safe assumption. It was a convenience, a shorthand, a shadow cast by deeper structures that did not resemble objects at all. What remained was a question physics could no longer avoid. If matter is wave-like and waves are not things, then what exactly is it that exists between interactions? And once that question is asked, the notion of particles begins to unravel, not violently but inexorably, into something far stranger than solidity ever allowed. A single electron is fired toward a barrier with two narrow openings. Behind it, a detection screen waits. Nothing about the setup is exotic. No extreme energies, no cosmic scales. Just one particle, one apparatus, and a choice that should not matter. Yet what happens next has been called the only real mystery in quantum mechanics. If electrons were classical particles, tiny objects moving through space, then each electron should pass through one slit or the other. Fire enough of them, and two bright bands should appear on the screen, directly behind the slits. This is not an assumption, it is geometry. But that is not what happens. When electrons are sent one at a time, slowly enough that no two ever interact, something extraordinary unfolds. Each electron arrives at the screen as a single localized dot. There is no ambiguity in the detection. One electron, one point. Yet as more and more electrons are recorded, those dots do not accumulate randomly. They assemble themselves into a pattern, a precise pattern, a pattern of alternating bright and dark fringes, an interference pattern. No electron ever interferes with another. Each arrives alone. And yet the collective result is identical to what would be produced by a wave passing through both slits simultaneously. This is not metaphor, this is not interpretation, this is what the data shows. Richard Feynman, reflecting on this experiment, remarked that it contains the heart of quantum mechanics. Not because it is complicated, but because it is impossible to reconcile with any classical picture of reality. If you think you understand it, he said, you do not. The nightmare begins with a simple question. Through which slit did the electron pass? If it went through the left slit, then the pattern on the screen should be consistent with particles traveling through that opening alone. If it went through the right, the same. But the observed pattern demands that the electron behave as though it went through both. Not sequentially, not partially, but in a way that defies the idea of location itself. The electron does not split. It does not smear, it does not divide its charge or mass. When detected, it is whole, indivisible, point-like. Yet the path it takes cannot be described as a single route through space. Attempts to rescue classical intuition only deepen the paradox. Suppose the electron really does choose one slit, but something else, some hidden wave, passes through both. That wave then interferes with itself and guides the particle to the detection point. This idea, appealing at first glance, runs into immediate trouble. Because the moment we attempt to detect which slit the electron passes through, the interference pattern vanishes. Place a detector at one slit, even one that barely interacts with the electron, and the pattern collapses into two classical bands. The wave-like behavior disappears. The electron behaves like a particle again.
No mechanical disturbance is required. No force strong enough to alter the electron's motion. The mere availability of which path information is sufficient.
This is not a technological limitation, it is a rule. The electron does not tolerate being watched. The act of measurement, of extracting information about the path, destroys the interference. Not because the electron is physically jolted, but because the conditions that allow wave-like behavior no longer exist. This leads to a conclusion that cannot be softened. There is no classical trajectory. Between emission and detection, the electron does not follow a well-defined path through space. It does not travel like a tiny projectile. It does not move through a sequence of positions that could, even in principle, be reconstructed. The question, where was the electron before it hit the screen, has no answer that respects the rules of the theory. This is not ignorance. It is not that we lack information. The theory itself forbids the question. In classical physics, motion is a story of continuity. Objects trace paths. Even when unobserved, those paths exist. In quantum mechanics, this picture breaks down. Motion becomes something else entirely, an evolution of probabilities rather than positions. The electron's wave function spreads through both slits, explores all available paths, interferes with itself, and then, without warning, yields a single outcome. The detection does not reveal a pre-existing location, it creates one. This is the aspect that many find intolerable. Reality, it seems, does not merely reveal itself through measurement. It responds to it. The experiments performed by Akira Tonomura and his colleagues in the late 20th century removed any remaining doubt. Using highly controlled electron sources, they demonstrated interference patterns forming one electron at a time, under conditions where no classical explanation could survive. The results were not statistical tricks. Each dot on the screen was recorded individually. The pattern emerged gradually, inexorably, as if guided by an invisible hand. The hand, it turned out, was not a force, it was a rule. Electrons behave according to wave equations until they are forced to behave otherwise. They are not objects traveling through space, they are processes unfolding through possibilities. The nightmare deepens when one considers what this implies for causality and motion. If an electron does not take a path, then how does it get from source to screen? The question assumes a picture that no longer applies. The electron is not something that moves through space in the classical sense. It is something that evolves. And evolution in this context does not mean change over time in a definite place. It means the transformation of a probability structure defined over all possible places. This is why classical analogies fail. There is nothing like this in everyday experience. No macroscopic object behaves this way. The brain, tuned for survival in a classical world, reaches instinctively for images that simply do not exist. What the double-slit experiment reveals is not a quirk of electrons. It is a structural feature of reality at the quantum scale. Localization is not fundamental. Trajectories are not real. Motion, as we understand it, is not how quantum objects behave. Particles, once thought to be the most basic ingredients of the universe, turn out to be the least reliable guides to what is actually happening. The electron is not a thing that travels. It is a phenomenon that occurs. And once that realization takes hold, the comfortable picture of the universe as a collection of moving objects dissolves. What remains is something far stranger, a world where outcomes are real, but the stories we tell between them are inventions. This is the double-slit nightmare, not because it is complicated, but because it forces us to abandon the very idea that reality unfolds as a sequence of definite events in space and time. And if that is true for a single electron, then the consequences extend far beyond the slits, far beyond the screen, and far beyond the notion that particles are the foundation of the world. The moment physics accepted that particles do not travel along definite paths, it inherited a far more disturbing question. If quantum objects are not things moving through space, then what exactly does the theory describe? The answer arrived in the form of an equation, not an image, not a mechanism, an equation. In 1926, Erwin Schrödinger wrote down a mathematical rule that governs how quantum systems evolve over time. At first glance, it looked familiar. It resembled wave equations already known from classical physics. It was continuous, smooth, deterministic in its own way. Schrödinger himself believed he had restored sanity to the quantum world. He imagined his equation described a real physical wave, perhaps an electron smeared out in space like a cloud. He was wrong, and the correction would change the meaning of reality itself. The Schrödinger equation does not describe the motion of objects. It does not tell us where a particle is or how fast it is moving. What it evolves is a mathematical entity called the wave function, usually denoted by the Greek letter psi. Psi is not a wave in space like a sound wave or a water wave. It does not vibrate matter. It does not carry energy in the classical sense. It is a function that assigns a complex number to every possible configuration of a system. For a single particle, that means every point in space. For multiple particles, it means a space so vast it cannot be visualized. This alone should give pause. The wave function does not live in ordinary three-dimensional space. It lives in an abstract space of possibilities, and what it encodes is not what is, but what could be. This was the conceptual break that many physicists resisted. Initially, Schrödinger hoped psi itself was physically real, a spread-out charge or mass density. But this interpretation collapsed almost immediately. Experiments showed that electrons do not smear their charge across space. They arrive whole, always localized, always indivisible. The wave function, it turned out, was not a material substance. The decisive reinterpretation came from Max Born. Born proposed something radical but precise. The wave function does not describe reality directly. Instead, its absolute square gives the probability of finding a particle in a particular location when a measurement is made. This was not an intuitive leap. It was a concession to the data. Born's rule worked. Every experiment confirmed it. The mathematics predicted outcomes with astonishing accuracy. But the price was enormous. Quantum theory no longer described what exists. It described the probabilities of events. This is where the wave function problem truly begins. Why probabilities? In classical physics, probabilities reflect ignorance. If you do not know the exact position and velocity of a particle, you assign probabilities. But the particle itself has definite values regardless of your knowledge. Probability is subjective. Reality is objective. Quantum mechanics does not allow this separation. Even when you know everything the theory permits, when you have complete knowledge of the wave function, you still cannot predict individual outcomes. The probabilities are not placeholders for missing information. They are fundamental. The wave function is not a catalogue of hidden facts. It is the most complete description available. And yet, it yields only likelihoods. This means that quantum theory at its core does not tell us what happens. It tells us what may happen and how often. The discomfort deepens when one examines the structure of psi itself. The wave function is generally complex-valued, meaning it involves imaginary numbers. These are not artifacts that can be ignored. They are essential. Interference, entanglement, and all non-classical behavior arise from the way these complex amplitudes combine. But imaginary numbers are not physical quantities. You cannot measure them directly. You cannot observe psi. You can only observe outcomes, detections, clicks, marks on screens. The wave function exists in a strange limbo. It governs reality, yet it is not itself observable. It evolves smoothly according to the Schrödinger equation, yet it produces abrupt, discontinuous events when measurements occur. This split lies at the heart of the problem. Between measurements, psi evolves deterministically. Given the wave function at one moment, the Schrödinger equation tells you exactly what it will be at the next. There is no randomness in this evolution, no collapse, no ambiguity. And then, suddenly, a measurement happens. The smooth evolution halts. One outcome occurs. The wave function appears to collapse to a new form consistent with that outcome. The probabilities vanish, replaced by a fact. But the Schrödinger equation does not describe this collapse. It has no place for it. Collapse is not part of the fundamental dynamics. It is an added rule, an instruction that tells us how to connect the mathematics to experience. This is not a minor technicality. It is an ontological fault line. Does the wave function physically collapse? Or is collapse merely an update of knowledge? If psi is real, then collapse looks like a violent, instantaneous change across space. If psi is not real, then what exactly is evolving according to the equation? Quantum mechanics refuses to answer cleanly. The theory works with extraordinary precision. It predicts atomic spectra, chemical bonds, semiconductor behavior, nuclear reactions. But it remains silent on what the wave function is. Is it a physical field, a state of knowledge, a bookkeeping device, a representation of tendencies? Different interpretations answer differently, but the mathematics itself is indifferent. This is why the wave function problem marks a shift from experiment to ontology. The experiments are no longer in doubt. The data is overwhelming. The problem is not what happens, but what it means. If psi is merely a tool for calculating probabilities, then quantum mechanics is not a description of reality, but a description of our expectations. Reality itself remains hidden behind the formalism. If psi is real, then reality is not made of objects in space, but of something abstract, high-dimensional, and profoundly counterintuitive. Either option is unsettling, and this tension cannot be resolved by better instruments or larger accelerators. It is not an empirical gap, it is a conceptual one. The wave function forces a rethinking of what it means to describe the world. Classical physics describes states of affairs. Quantum physics describes structures of possibility. It does not say, this is where the particle is. It says, if you look here, this is how likely you are to find it. The object has been replaced by the outcome, the thing at the event. This is why attempts to cling to classical realism falter. One can no longer imagine particles carrying hidden properties that determine outcomes in advance. The formalism does not support it, and attempts to add such properties lead to conflicts with experiment. The wave function problem is not a technical nuisance to be solved later. It is the moment physics realizes that its most successful theory does not describe reality in the way we instinctively expect. The universe, according to quantum mechanics, is not a collection of things with definite properties. It is a structure of probabilities evolving according to precise rules, punctuated by events that crystallize possibilities into facts. What exists between those events is not nothing, but it is not something that fits into classical language either. And once this realization settles in, a new question becomes unavoidable. If the wave function is not an object and particles are not trajectories, then what exactly is the fabric of reality made of? The answer, whatever it is, will require us to abandon not just old equations, but old instincts about what it means for something to be real. Quantum mechanics has delivered a series of shocks. Particles are not particles, waves are not waves. Energy comes in discrete packets. Electrons interfere with themselves. The wave function evolves in a high-dimensional space of possibilities rather than actual locations. And yet, for all its predictive power, the theory encounters a point where it abruptly confronts the act of observation itself. This confrontation is known as the measurement problem. At its heart lies a single, unsettling question: what happens when a quantum system is observed? The wave function evolves deterministically according to the Schrödinger equation, spreading smoothly and continuously, encoding all possible outcomes. And then, suddenly, a measurement occurs. The probabilities vanish, replaced by a single result. One dot on a screen, one electron detected, one photon absorbed. Where does this single outcome come from? The formalism offers no mechanism. Schrödinger's equation does not describe this transition. This abrupt collapse of the wave function is nowhere contained in the theory's evolution laws. Yet without it, there is no connection between the mathematics of probability amplitudes and the reality we experience. Physics predicts statistical distributions perfectly, but it cannot explain how one individual outcome manifests. Niels Bohr, one of the founding architects of quantum theory, confronted this conundrum with a form of pragmatic philosophy. Bohr argued that the wave function is not a direct description of reality, but a tool for organizing knowledge about potential experimental outcomes. Measurement is not a passive act. It defines the conditions under which properties like position or momentum become meaningful. Until a measurement occurs, it is meaningless to speak of a particle having a specific position or velocity. This view became the cornerstone of the Copenhagen interpretation. According to this interpretation, the wave function collapse is not necessarily a physical process. It is a reflection of the transition from the abstract realm of quantum possibilities to the concrete realm of classical outcomes. In this sense, collapse is less a sudden event in the world and more an update in our description of it. The observer, therefore, occupies a central role, not because consciousness magically alters the universe, as some sensationalized accounts claim, but because the theory only predicts outcomes within the context of an experimental arrangement. A quantum property does not exist in isolation. It only exists in relation to the conditions imposed by measurement. Reality at the quantum level is inherently relational. This stance has profound implications. It denies that the wave function represents an objective physical entity in the traditional sense. The electron is not somewhere really until it is measured. Its reality is not intrinsic, but contingent, defined by interaction. The world, at its most fundamental level, becomes anti-realist. Properties exist only when observed or defined by an experiment. Yet not all physicists accepted this anti-realist turn. Critics objected that it relegates the universe to an epistemic shadow where the objective existence of things is subordinated to the observer's knowledge. Albert Einstein famously rejected this view, insisting that the moon exists even when we are not looking at it. To him, the Copenhagen interpretation was a philosophical compromise, a surrender to mystery rather than a complete explanation. The conflict between realist and anti-realist perspectives is sharpened by the formalism itself. The Schrödinger equation allows for superpositions. A quantum system can exist in multiple states simultaneously. Schrödinger illustrated the absurdity of extending this principle to the macroscopic world with his famous thought experiment, the cat that is both alive and dead until observed. While the cat exaggerates the scale, it illustrates a genuine dilemma. If the wave function is real, collapse must be a physical process. If collapse is not physical, then how does one reconcile the formalism with definite outcomes? Various attempts have been proposed to clarify the collapse. Some interpretations, like objective collapse theories, posit that wave functions spontaneously collapse without observation, driven by mechanisms not yet fully understood. Others, like the many worlds interpretation, deny collapse entirely, suggesting that all outcomes occur in branching universes. The Copenhagen interpretation, by contrast, remains silent on the mechanism, instead emphasizing the inseparability of measurement and system. This ambiguity is not mere philosophical hair-splitting. It affects the ontology of the universe itself. If collapse is physical, then reality undergoes discontinuous changes. If it is informational, then reality may be a network of potentialities that crystallize only in the act of interaction. Either way, the familiar picture of a universe composed of discrete, independent objects is under threat. The anti-realist stance also redefines causality and temporality. Until an observation is made, the evolution of a quantum system is described only probabilistically. There is no definite trajectory. Past and future are encoded in the same wave function. The act of measurement selects a specific history out of many possibilities, creating a temporal asymmetry that has no classical analog. Moreover, the role of the observer need not be limited to humans. Any interaction that forces a system into a definite state, a photon hitting an electron, a molecule scattering off a surface, counts as a measurement in the Copenhagen sense. Observation, then, is a process, not a consciousness-dependent miracle. But the boundary between quantum indeterminacy and classical definiteness remains ambiguous, a blurry frontier where reality seems to be defined by context rather than substance. In practical terms, this interpretation works astonishingly well. Experiments are predicted with extraordinary precision. Atomic clocks, semiconductors, lasers all rely on calculations consistent with a formalism in which collapse is a rule applied when interactions occur. But the conceptual tension persists. The theory succeeds. Our intuition fails. The question of whether collapse is real or illusory remains a central puzzle. The wave function problem evolves here into a confrontation with philosophy. It asks us to reconsider what it means for something to exist. Does the universe hold definite properties independently of measurement, or is our experience of reality inseparable from the acts that probe it? The Copenhagen view suggests the latter, presenting a universe that is less an assembly of objects than a dynamic interplay between potential and actuality, and yet the tension is palpable. The collapse, or the lack thereof, forces us to confront the limits of knowledge, the interplay between observer and system, and the fragility of the categories that classical physics once took for granted. What we see, what we detect, is real, but what lies beneath, the wave function itself, remains a shadowed domain of possibility, of probability, of potential. In this sense, the Copenhagen interpretation is both a guide and a warning. It guides us by telling us how to make predictions, how to connect abstract mathematics with observable phenomena. It warns by demonstrating that our classical assumptions about reality, object permanence, determinism, independent existence, cannot survive intact. Collapse, then, is either a real violent event in the fabric of reality or an emergent artifact of how knowledge is updated. The theory does not resolve which. The experimental evidence does not dictate one over the other. It only enforces a sobering truth. At the heart of quantum mechanics lies an irreducible ambiguity, a fundamental tension between what is observed and what exists independently of observation. The question lingers, haunting both physicist and philosopher alike. When we watch the world, do we shape it? Or do we simply uncover what was always there, hidden behind a veil that mathematics alone cannot lift? The wave function has brought us to the brink of a deeper mystery. And whether it collapses or merely appears to, we are compelled to ask, what in the end is the substance of reality itself? Imagine a universe in which nothing ever truly collapses, where the wave function never snaps, never yields a single outcome, where the quantum rules that govern probabilities are absolute and uninterrupted. In such a universe, the very notion of a particle, solid, localized, persistent, loses its meaning entirely. Perhaps we begin to wonder, particles never existed at all. In 1957, Hugh Everett III proposed a radical solution to the quantum conundrum. He asked a simple but daring question. What if the collapse of the wave function is an illusion? What if the deterministic evolution dictated by the Schrödinger equation continues everywhere, always? In this vision, the universe does not select one outcome when a measurement occurs. Instead, every possible outcome occurs in a branching cascade of realities. This is the many worlds interpretation. There is no wave function collapse. There is no special role for the observer. There is only the universal wave function, evolving smoothly and deterministically, encompassing every conceivable possibility. A single electron passing through a double-slit apparatus does not choose one path. Instead, the universe splits into multiple non-interacting branches, each containing a version of the electron that traveled one slit or the other. From this perspective, the world we perceive, a table, a chair, an electron appearing at a screen, is just one branch among countless others. The wave function is real in the most literal sense. Particles are not fundamental entities but emergent phenomena relative to the branch in which an observer exists. Their properties, including position, momentum, and energy, are branch-dependent. They are features of a local perspective, not universal building blocks. What does it mean to say that particles never existed? In this framework, the universe is not a collection of tiny balls moving through space. It is a vast, ever-branching superposition of possibilities. Electrons do not traverse trajectories. Photons do not travel as discrete bullets. All observable behavior emerges from the underlying universal wave function, manifesting as patterns within branches. Particles are a convenient shorthand, an effective description valid only within a localized perspective. Experimental phenomena that once demanded particles can be reinterpreted entirely in terms of branching wave functions. The double-slit experiment, which confounded classical intuition for decades, becomes a straightforward illustration. The interference pattern arises because the electron exists in multiple branches simultaneously. The which path question dissolves because every path is realized in some branch. There is no need for collapse, no need for a special act of measurement. Observation is simply the branch in which a given outcome is recorded. Everett's idea resolves many conceptual tensions of quantum mechanics, but it comes at a philosophical cost. Reality becomes unimaginably vast. The universe contains an enormous, continuously proliferating number of branches, each as real as the one we inhabit. There is no privileged branch, no true outcome. The world is not singular but deeply plural. Determinism is preserved globally, but locally it appears probabilistic because we inhabit only one branch at a time. Sean Carroll, in Something Deeply Hidden, emphasizes that the many worlds perspective restores realism without invoking particles as fundamental entities. The universe is real. The wave function is real. Our experience of discrete objects is real, but only relative to the branch in which we exist. Quantum events are not particles popping in and out of existence. They are patterns emerging from a branching structure that spans all possibilities. From this viewpoint, the conceptual discomfort surrounding wave function collapse evaporates. There is no jump from probability to actuality. There is only continuous evolution, unbroken and comprehensive. Measurement does not enforce reality. It merely situates an observer in one branch of a larger deterministic structure. Apparent randomness is a reflection of our limited perspective, not a feature of the underlying physics. Yet despite its elegance, Many Worlds is radical. It eliminates familiar intuition about objects and particles, replacing them with a universe of branching histories, where solidity and localization are emergent illusions. Space and time persist, but the inhabitants of each branch experience reality as if it were classical. The rest of the multiverse, however, remains hidden, unobservable, and unfathomably vast. Experiments cannot yet distinguish many worlds from interpretations that invoke collapse. The predictions for outcomes are identical at the level of statistics. But philosophically, the implications are profound. The universe does not rely on discrete objects. Particles are convenient labels, not fundamental ingredients. Reality itself is an uninterrupted tapestry of possibilities, with branches unfolding wherever quantum events occur. In this vision, the classical world is a pattern within a larger, more abstract structure. Objects, matter, particles, these are not primitive elements of the universe, but emergent phenomena arising from the constraints of branch-relative perspectives. What we once thought of as building blocks are shadows cast by the universal wave function. The electron is no longer a thing traveling through space. It is a manifestation of patterns in a higher dimensional structure of existence. The radical elegance of Many Worlds lies in its simplicity. Remove collapse, accept the universal wave function as real, and the rest follows. No mysteries about measurement, no observer-induced jumps, no arbitrary distinctions between wave and particle. Everything is wave function everywhere, all the time. Particles exist only within local branches, not universally. The implications extend beyond physics. Philosophically, Many Worlds demands a reconsideration of what it means for something to exist. Is reality what we see, or the totality of all branches? Is identity tied to a single history, or dispersed across an immense multiversal structure? Determinism applies globally, yet we experience uncertainty. Observers are embedded patterns within the wave function, never separate from it. Hugh Everett's radical proposal forces us to abandon the comforting idea that particles are fundamental, enduring objects. Instead, we are left with a universe of pure evolution, structured by the Schrödinger equation, where all possibilities coexist and reality is revealed only through our branch-relative perspective. It is a world that is deterministic, yet disorienting, structured yet unbounded, continuous, yet yielding the discrete experiences we mistakenly call particles. In this universe, the question of what is real acquires a new depth. Reality is not a collection of tiny building blocks, nor a series of localized events. Reality is the universal wave function itself, a vast, coherent, and ever-branching structure in which particles never existed as fundamental entities. Everything we experience is a local manifestation of that deeper, continuous, and astonishingly intricate whole. The Many Worlds interpretation does not merely reinterpret quantum mechanics, it transforms our conception of existence. It challenges every assumption about substance, location, and individuation. Particles are gone, waves are everything, and the universe in its full extent is unimaginably richer than any classical intuition could ever allow. To understand the universe at its most fundamental level, one must abandon the comforting notion of things moving from one place to another. Particles, waves, trajectories, these are all concepts rooted in classical intuition. But quantum mechanics, in its full depth, reveals a world where none of them are strictly necessary. Reality does not consist of objects traveling along paths. Reality consists of paths themselves, a vast summation of possibilities. This radical perspective was formalized by Richard Feynman in the 1940s through his path-integral formulation of quantum mechanics. Instead of asking, "Where is the particle?" or "What wave propagates?" Feynman asked, "What is the sum of all possible histories connecting one point to another?" Every conceivable path that a quantum object could take contributes to the final outcome. No path is privileged, no trajectory exists in isolation. Each contributes a complex amplitude, a number encoding both magnitude and phase. Consider a simple particle moving from point A to point B. Classical intuition imagines a single definite path, a straight line perhaps, or a trajectory curved by forces. In Feynman's picture, the particle explores every imaginable path simultaneously: straight lines, loops, zigzags, even wildly contorted trajectories that seem impossible in classical terms. Each path adds its own wave-like influence. When all paths are summed, the resulting interference produces the probabilities that we observe.
The mathematics is elegant and terrifying. Paths that reinforce one another amplify the likelihood of certain outcomes. Paths that cancel each other reduce the likelihood to near zero. The interference patterns of the double-slit experiment emerge naturally. The electron does not choose a slit. Instead, every path through both slits contributes, and the resulting pattern reflects the sum of all amplitudes. There is no contradiction between particle-like detection and wave-like interference, because the formalism never relies on particles in the first place.
The Feynman path integral dissolves the distinction between particles and waves. The electron is neither a tiny object nor a smeared-out wave. It is a collection of histories, a process, a summation of all possible motions weighted by probability amplitudes. Trajectories, localization, and paths as classical objects are merely emergent approximations, valid only when the number of contributing histories becomes dominated by a single path, as in the macroscopic world. This framework also clarifies why classical mechanics works at everyday scales. When the action along paths is large compared to Planck's constant, the contributions from wildly divergent paths interfere destructively. Only paths near the classical trajectory constructively interfere, producing behavior consistent with Newtonian expectations. In this sense, classical reality emerges as a statistical shadow of an underlying, profoundly richer quantum process. Feynman's approach offers more than a computational tool. It suggests a new ontology. Reality is not made of things, it is made of processes. The universe unfolds as a summation over histories, as a complex interwoven web of possibilities. Events occur where amplitudes interfere constructively. What we perceive as objects, particles, or waves is a local, emergent feature arising from the coherent summation of countless quantum possibilities. Experiments reinforce this view. Electron interference, molecular diffraction, and even quantum tunneling are naturally described by path integrals. Each phenomenon, previously perplexing under particle or wave models, becomes comprehensible as the result of cumulative histories. Tunneling, for example, no longer requires a particle to borrow energy or a wave to leak through a barrier. Instead, it is the interference of multiple paths, including ones forbidden in classical mechanics, that produces the observed probabilities. Moreover, the path integral formalism unifies seemingly disparate aspects of quantum theory. Fields, particles, and interactions are all manifestations of underlying histories. In quantum field theory, interactions are calculated by summing over all possible configurations of fields, which can be interpreted as sums over histories of excitations. The ontology shifts. The universe is less a static collection of entities and more a dynamic tapestry of possibilities unfolding through consistent rules. The philosophical implication is staggering. If reality is a sum over histories, then the question, what is real, loses its usual meaning. Classical objects, positions, and trajectories are approximations valid only in the macroscopic limit. At the fundamental scale, there are no privileged paths, no singular events until interactions occur, and no objects in the classical sense. Everything is process. Everything is interference. The universe is a continuously evolving ensemble of potentialities, manifesting observable outcomes only where paths reinforce one another. This shift has consequences for understanding time, causality, and determinism. Each path extends across space-time. The future is not predetermined as a single trajectory, but exists as a superposition of histories. Probability amplitudes evolve according to the Schrödinger equation, and outcomes are the cumulative result of interfering possibilities. Determinism, in this view, is global and exact in the wave function, yet locally probabilistic when observed. Feynman's path integrals also illuminate why the classical intuition of motion fails at small scales. Electrons do not move through space in the way that planets orbit stars. They are not tiny billiard balls tracing defined paths. Motion is an emergent phenomenon, arising from the collective interference of countless paths. Localization occurs only upon interaction with a measurement apparatus, giving the illusion of a trajectory. Between measurements, the electron has no position, no path, no classical existence. In this sense, the path integral formulation replaces ontology with process. The building blocks of the universe are not things, not particles, not waves, not even fields in the traditional sense. They are histories, amplitudes, possibilities. Events emerge from the sum over these possibilities, and reality is the interference pattern they produce. The universe, therefore, is an intricate network of processes, not a collection of objects. Particles, waves, trajectories, and fields are convenient labels, patterns that emerge under specific conditions. At the most fundamental level, all that exists is the sum over histories, the continuous unfolding of quantum possibilities. By abandoning objects in favor of paths, physics opens a new window into the fabric of reality. The focus shifts from what is to what could be, from discrete things to evolving possibilities, from solid particles to patterns of interference. The world we perceive, stable, localized, tangible, is not the foundation. It is the emergent consequence of a universe built from processes, probabilities, and paths. In this framework, quantum mechanics ceases to be a theory about particles or waves. It becomes a theory about the evolution of possibility itself. The electron is not a tiny object traversing a path. It is a collection of paths. Reality is the sum of all possible histories, and our classical world is the shadow these histories cast. The universe is not a collection of particles, not in the sense we once believed, not even waves in the classical or quantum sense. Modern physics has revealed a deeper substratum, an ocean that stretches across all of space and time, continuous, dynamic, and profoundly counterintuitive. This is the realm of quantum fields. Quantum field theory, or QFT, is the framework that unites quantum mechanics with special relativity, providing the foundation for our most accurate descriptions of reality. In this theory, the fundamental entities are not objects moving through space, nor wave functions oscillating in abstract spaces. The fundamental entities are fields, pervasive, omnipresent, and inexorably real. Every particle we have ever detected is, in fact, an excitation of a field. The electron, the photon, the quark, all are manifestations of underlying fields that fill every corner of the cosmos. Imagine, if you will, a vast invisible ocean stretching infinitely in every direction. Ripples travel across it. Waves rise and fall, sometimes interacting, sometimes colliding, creating patterns that can persist or vanish. In QFT, the ocean is a quantum field, and the ripples, the quantized excitations, are what we detect as particles. There are no fundamental particles, only excitations. When an electron appears in an experiment, it is not a tiny object arriving from somewhere. It is the local excitation of the electron field, a fluctuation in a continuous medium that exists everywhere. Mathematically, QFT describes these fields using operators that act across space and time. Creation operators generate excitations, particles, while annihilation operators remove them. The language is abstract, but the implication is striking. Particles are not pre-existing things. They are events, processes, disturbances in the fabric of the field. An electron is not a thing that exists independently. It is the field vibrating in a specific quantized way. This perspective overturns centuries of intuition. Classical physics taught that particles are the building blocks of matter. Quantum mechanics complicated that picture with wave-particle duality, probability, and the role of measurement. But QFT dissolves the concept entirely. Particles, as discrete localized objects, are emergent phenomena, meaningful only in the context of interactions that excite the underlying fields. Consider light. Classical physics imagined it as a wave traveling through a medium, then later as a stream of photons. In QFT, the electromagnetic field pervades all space. Photons are merely the quantized excitations of this field. When an atom emits a photon, it is not releasing a pre-existing particle. It is transferring energy into the electromagnetic field, creating a localized excitation that propagates and eventually interacts with another system. The particle-like behavior emerges only when the field interacts with a detector, producing a discrete event. This shift has profound consequences for our understanding of reality. It suggests that the objects and particles we see are shadows of a deeper, more continuous layer. The solidity of matter, the discreteness of charge, even the conservation of energy. These are all properties emerging from field dynamics, not inherent features of fundamental particles. Fields are the substrate, particles are the observable phenomena. Quantum fields also unify forces and matter greatly. In the standard model of particle physics, each fundamental particle corresponds to a field. The electron to the electron field, the photon to the electromagnetic field, the quarks to their respective fields. Interactions between particles are not collisions of little balls. They are interactions between fields, the exchange of excitations mediated by other fields, such as the photon field for electromagnetic forces. This explains why, at high energies, particles can be created or destroyed. Energy input into a field can generate new excitations, producing what we interpret as particle creation, while annihilation removes them, returning the energy to the field. The ontological shift is dramatic. Particles are no longer fundamental, nor even permanent. They are transient manifestations of something far deeper, a continuous, unbroken network of fields that underlies everything. The universe is not a collection of objects in space. It is a symphony of fields vibrating and interacting, and what we call matter or energy is the pattern of excitations in that symphony. The experimental evidence for this view is overwhelming. High-energy particle colliders, such as the Large Hadron Collider, do not smash particles into one another to reveal pre-existing entities. They energize fields, producing excitations that we detect as particles. The discovery of the Higgs boson, for example, was not the finding of a solitary particle. It was confirmation of the Higgs field and its role in endowing other fields' excitations with mass. Every particle we observe is a signature of field behavior, an event in an ever-present invisible lattice. Moreover, QFT resolves long-standing puzzles of quantum mechanics. The apparent paradoxes of particle-wave duality, localization, and creation or annihilation of particles become natural when one accepts that only fields are fundamental. Interference patterns arise from the evolution of fields. particles appear localized because interactions with measurement devices excite quantized modes. Energy is quantized not because particles exist as discrete units, but because fields themselves support quantized excitations. Philosophically, QFT pushes us to abandon object-based metaphysics. The classical picture of a world built from enduring things is inadequate. Reality is not a universe of billiard balls, nor a collection of waves oscillating in space. Reality is a continuum of fields, obeying precise, probabilistic, and yet highly structured laws. Particles, objects, events, these are secondary, emergent phenomena arising from interactions and excitations. This perspective also reshapes our understanding of causality and interaction. Since fields extend through space and time, they can influence each other non-locally, giving rise to correlations that appear instantaneous, yet emerge naturally from the underlying field dynamics. Entanglement, once mysterious under particle metaphors, is simply a manifestation of correlations in field excitations. Particles are a bookkeeping convenience. The fundamental dynamics are continuous, relational, and field-based. The implications are staggering. Our classical notions of substance, location, and individuation must be revised. The world we see, the stable particles, the solid table, the discrete electron, is not fundamental. It is a pattern carved from an underlying ocean of fields. Particles are excitations, events, the flickers of a deeper reality. In a very real sense, there are no particles at all, only the symphony of fields. Quantum field theory, then, is the culmination of a long journey. From the Newtonian point mass, through waves and probabilities, through interference, collapse, and branching universes, we arrive at a vision where the solid particulate world dissolves entirely. The universe is continuous, pervasive, and profoundly more abstract than our senses suggest. Particles are merely the ephemeral manifestations of excitations in this continuous fabric. The ontology has shifted from object to process, from entity to field, from certainty to possibility. In embracing fields as fundamental, physics abandons classical intuitions completely. We are no longer observers of a universe made of discrete building blocks. We are witnesses to patterns arising from continuous, omnipresent, and interacting fields, the true substrate of reality. And in this vast, vibrating expanse, particles, once thought to be the indivisible foundation of matter, recede into the status of emergent, transient phenomena, flickering into existence only as the fields themselves allow. The universe, in its deepest structure, is not a collection of things. It is a continuous, dynamic sea of fields, and the events we call particles are merely ripples upon its surface. In our journey through the quantum realm, we have already abandoned particles as fundamental objects, recognizing them as excitations of omnipresent fields. But even this concession is not enough. Modern physics delivers yet another blow to classical intuition. The notion of localization, the idea that an object occupies a definite region in space, is fundamentally incompatible with relativistic quantum theory. Particles cannot be strictly confined. They cannot be pinned down. They cannot retain the identity that we instinctively attribute to them. This unsettling insight arises from what is known as Hagerfeld's theorem, formulated in the 1970s and 1980s by Gerhard Hagerfeld. The theorem demonstrates that if a quantum particle were perfectly localized in a finite region of space at one moment in time, relativistic causality would be violated. In simple terms, the particle would instantly have a non-zero probability of appearing arbitrarily far away, faster than light could travel. A perfectly localized state is mathematically incompatible with the combination of quantum mechanics and special relativity. The universe does not allow it. At first glance, this seems absurd. Our everyday experience is filled with objects that appear localized. An apple rests on a table, an electron is detected at a point in a cloud chamber. Yet the classical picture of a particle as a point-like object that travels through space cannot survive the relativistic quantum framework. Localization is always approximate. A particle is never truly confined. It is a delocalized excitation of a field that extends, in principle, infinitely. This delocalization is reinforced by the pervasive presence of vacuum fluctuations. Even the empty vacuum of space is not truly empty. Quantum fields undergo continuous fluctuations, constantly producing ephemeral pairs of excitations that flicker in and out of existence. These fluctuations mean that the concept of an isolated static particle is an illusion. A particle's presence cannot be separated from the restless, seething background of the quantum vacuum. The identity of an object is intertwined with a network of potential interactions and disturbances extending across space. The breakdown of localization also undermines classical identity. If a particle cannot be strictly confined, it cannot be said to occupy a unique location. If it cannot occupy a unique location, then the notion of a persistent thing moving along a defined trajectory collapses. Classical objecthood, the sense that a particle is a discrete entity with well-defined boundaries, is no longer tenable. The electron we measure is not a self-contained object. It is a manifestation of a field's excitation, distributed, relational, and inseparable from the underlying quantum and relativistic structure. Relativistic quantum mechanics further complicates the picture. In non-relativistic quantum theory, we can speak loosely of a particle's wave function being mostly in some region, with vanishingly small probabilities elsewhere. But once relativity enters, the wave function itself cannot be restricted to a finite region without allowing for superluminal propagation. The universe forbids absolute localization. No particle, no matter how we define it, can be entirely confined. Its identity is inherently smeared across space-time, an unavoidable consequence of the principles that govern nature. These insights are not mere mathematical curiosities. They have practical consequences for quantum field theory, particle physics, and our interpretation of reality. Particle detectors never observe perfectly localized entities. They record events, interactions between fields that appear discrete only because of the nature of measurement. The particle that arrives at a detector is a local manifestation of an extended, delocalized excitation. Its position is contextual, not intrinsic. Hagerfeld's theorem, together with the omnipresence of vacuum fluctuations, forces a radical re-evaluation of ontology. If particles cannot be localized, they cannot serve as the fundamental building blocks of matter. Classical notions of persistence, separability, and identity fail. The universe is not composed of tiny, solid things traveling through space. It is a tapestry of field excitations, probabilistic events, and relational interactions. Objects are emergent, approximate, and context-dependent. This destruction of objecthood resonates with other quantum insights. Wave function collapse, many worlds branching, path integrals, and field excitations all converge on a single point. What we perceive as a particle is never an independently existing localized object. It is a process, a pattern, a temporary manifestation of deeper structures. Relativity reinforces this conclusion by forbidding absolute localization and enforcing a universal connection between space, time, and the non-local nature of quantum states. Even in the macroscopic world, where objects appear solid and localized, these principles operate beneath the surface. Classical localization emerges as an approximation, a statistical result of countless underlying excitations behaving coherently. The solidity of a chair, the position of a planet, the trajectory of a baseball, all are emergent patterns built upon a substrate that defies individual identity and confinement. The implications are profound for our understanding of reality. We are forced to abandon not only the notion of fundamental particles, but also the comforting assumption that the universe is made of separable, persistent objects. Reality is not a collection of things with sharp boundaries. It is a dynamic web of field excitations, potentialities, and interactions. Localized phenomena are approximations, not absolutes. Identity is contextual, relational, and inherently fuzzy. In this sense, Hegerfeld's theorem is more than a technical result. It is a conceptual milestone, marking the point at which classical intuitions about individuality, separability, and localization finally break down. The classical particle, an object confined to a single location at a single time, is revealed to be a fiction, a useful approximation, but no more fundamental than a shadow cast by a deeper, unobservable structure. The death of localization completes the journey from classical realism to a world defined by relational processes, emergent phenomena, and continuous fields. The universe does not provide us with particles to hold, nor with trajectories to trace. It provides patterns of interaction, excitations of fields, and events that crystallize possibilities. Objecthood, once assumed to be the foundation of reality, is revealed to be a derivative, emergent, and ultimately fragile concept. At the end of this realization, we are left with a disorienting yet astonishing vision. The universe is not a collection of discrete things. It is a continuous, interconnected web, where apparent solidity, localization, and identity emerge only in the context of measurement, interaction, and approximation. Particles, as we once imagined them, do not exist. They never truly did. Reality, at its core, is fluid, relational, and profoundly non-classical. Gerhard Hegerfeld's work reminds us that even the notion of where a particle is cannot survive unexamined. The classical world of distinct, identifiable objects is an emergent illusion, resting atop a deeper quantum relativistic substrate that refuses to conform to our intuitive categories. In this universe, objecthood dies, and in its place arises a subtler, more complex, and far more beautiful reality. In classical physics, correlations are simple. One object influences another. If you measure the spin of a particle here, it reveals information about that particle and perhaps about something it has interacted with. The mechanism feels intuitive. Cause produces effect. Information travels along chains of particles. And reality consists of things with well-defined properties. But quantum mechanics forces us to abandon this intuition, revealing a deeper, more unsettling truth. Correlations can exist without any object carrying them. This is the essence of entanglement. Two quantum systems can become linked such that the state of one instantaneously correlates with the state of the other, no matter the distance separating them. Measure one, and the other is constrained. Yet neither particle travels information, neither carries a hidden instruction manual. There are no underlying things transmitting the effect. Reality in this view is relational, not particulate. John Bell formalized this insight in 1964 with what are now called Bell inequalities. He asked a question that went to the heart of the classical worldview. Could these correlations be explained by hidden variables, unobserved properties that particles carry with them from the past? If so, nature would retain an objective local reality. Particles would have definite properties independent of observation, and correlations would simply reflect this pre-existing information. Bell's inequalities, however, revealed a stark limitation. If local hidden variables existed, measurements on entangled particles would be constrained to satisfy certain statistical bounds. But quantum mechanics predicts violations of these bounds. The correlations are too strong, too precise, too non-local to be explained by any classical object-based model. Experimentalists rose to the challenge. In the 1980s, Alain Aspect and his colleagues performed the first rigorous tests of Bell inequalities using entangled photons. Their results were unambiguous. The correlations predicted by quantum mechanics occurred, and no hidden variable theory could account for them. Since then, increasingly sophisticated experiments, including loophole-free tests cited in the 2022 Nobel Prize announcements, have consistently confirmed that entanglement is a real, unavoidable feature of the universe. What do these results imply? They imply that the properties we measure, spin, polarization, or other observables, do not exist independently as attributes of individual particles prior to measurement. Instead, they exist only in relation to other systems. The universe is not composed of independently existing things carrying intrinsic properties. It is a network of relationships, a web of correlated possibilities that only manifest when interaction occurs. Entanglement thus forces a radical rethinking of reality. Classical objects with intrinsic identities, localized positions, and independent attributes are an approximation. At the quantum level, properties are emergent, contingent upon context, and inseparable from the web of correlations in which they participate. Particles are not carriers of correlation. Correlations exist prior to and independently of any presumed objects. This relational view has profound implications. In a sense, the universe is no longer a stage populated by actors. The actors themselves are defined by their interactions, by the entangled network of possibilities that connects them. Objects, as we imagine them, are emergent nodes within this network, temporarily isolated patterns in a continuous relational fabric. Consider two entangled photons separated by light years. Measure the polarization of one, and the other's polarization is instantly correlated. No signal travels between them. There is no hidden object shuttling information. The correlation is fundamental, a manifestation of the relational structure of reality itself. Space and distance do not limit these correlations. They exist because the universe is structured as a web of interdependent states, not as a collection of isolated particles. From the standpoint of ontology, entanglement without things undermines any object-centric conception of reality. It replaces substance with relation, isolation with connectivity, and independent existence with mutual definition. In the quantum world, what is real is not the particle itself, but the relational properties it participates in. Existence becomes a networked phenomenon. Events, correlations, and interactions define the content of reality. This insight extends beyond two-particle systems. In complex quantum networks, entanglement can span many particles, forming intricate patterns of correlation. Each node of this network does not possess an independent identity. Its properties are defined through the entangled web in which it participates. The classical idea of a particle as a self-contained entity is obsolete. Reality is fundamentally holistic, relational, and non-local. Even quantum information theory, developed in the past few decades, reflects this shift. Information is no longer seen as encoded in particles, but in correlations between systems. Quantum teleportation, superdense coding, and entanglement-assisted protocols all exploit relational properties that exist independently of individual objects. The lesson is clear. In the quantum universe, correlations are the currency of reality, not particles. This relational ontology resonates with previous quantum insights. Wave function collapse, path integrals, and field excitations all suggest that objects are emergent patterns rather than fundamental constituents. Entanglement drives this realization home. It demonstrates that even the strongest correlations cannot be attributed to pre-existing things, but are encoded in the structure of the universe itself. Thus, at the deepest level, we are compelled to abandon classical intuitions entirely. Reality is not composed of particles carrying properties or moving along paths. It is a network of relations, a tapestry of correlated possibilities that manifest in measurement. Objects, solidity, localization, and identity all are emergent features, secondary to the fundamental interconnections that define the quantum world. Entanglement without things is more than a curiosity. It is a principle that reshapes our understanding of existence. It demands that we think relationally, that we accept that reality is structured around correlations rather than constituents. In this view, the universe is not a collection of objects bumping into one another, but a living web of possibilities, where the only thing that truly exists is the pattern of relationships. And so, Bell's theorem and the aspect experiments reveal a startling truth. At the heart of quantum mechanics, there are no objects carrying properties, only relations manifesting as observable correlations. The classical picture of discrete, independently existing entities is no longer viable. What is real is not the particle, not the field, not the trajectory. It is the network of entanglement itself, the relational fabric upon which all observable phenomena arise. In this relational universe, the classical dream of isolated objects is abandoned. Reality is defined by connection, by interdependence, and by the correlations that emerge without any underlying carriers. In the quantum world, things are secondary, relations are fundamental, and our perception of objects is merely the emergent shadow of an infinitely richer relational structure that defines the very essence of existence. Perhaps the most unsettling question of all is not whether particles exist, but whether the word particle itself misleads us. Across centuries, physicists and philosophers have clung to the term, picturing tiny, solid objects moving through space. Yet modern physics, the cumulative insight of quantum mechanics, field theory, and entanglement, suggests that the very language of particles may be an artifact of human thought rather than a mirror of reality. What if particle is not a descriptor of nature, but a shorthand, a linguistic convenience that shapes our imagination more than it captures the world? Critiques in journals such as Europhysics News have called attention to this subtle but profound point. As quantum theory matured, the correspondence between the word particle and the underlying physical ontology weakened. Light is not a particle. Matter is not a particle. Fields, wave functions, path integrals, and entanglement reveal that what we measure as particles are emergent phenomena, events in a network of possibilities, patterns of interaction, rather than independently existing objects. The term particle persists because it is pragmatically useful, not because it corresponds to a fundamental entity in the universe. Philosophers of science have long grappled with this tension between language and reality. Hilary Putnam, for instance, emphasized the model-dependent nature of scientific terms. A term like electron or particle acquires meaning only within a theoretical framework. Outside that framework, the word does not point to a universal object. It points to a conceptual tool for prediction and explanation. Scientific language, in other words, is inseparable from the models that give it life. When the model changes, as it has repeatedly from Newtonian mechanics to quantum field theory, the terms we inherited from older models may no longer correspond to reality. This is not merely a philosophical abstraction. In quantum field theory, for example, particles are excitations of fields. They behave in ways that classical intuition would call particle-like under certain circumstances, localized impacts in detectors, quantized energy transfers, but in the deeper mathematical description, they are not fundamental. Calling them particles imposes a classical narrative onto a fundamentally non-classical reality. It is the language itself that evokes solidity, individuality, and separability, even when the physics does not support these notions. The tension extends to quantum mechanics more broadly. Consider the double-slit experiment. An electron appears as a localized dot on a screen, yet it produces an interference pattern only when unobserved. We call it a particle when we detect it, a wave when it interferes, but these labels are contingent, not intrinsic. They are artifacts of the human attempt to categorize a process that resists categorization. The word particle is a placeholder in a story we tell ourselves to reconcile classical intuition with quantum observation. Model-dependent reality, a concept explored in philosophy of science, emphasizes that what we take as real is inextricably linked to the theoretical frameworks we use to describe it. In the classical era, particles were real because Newtonian mechanics modeled them as point masses obeying deterministic laws. In the quantum era, particles remain a useful shorthand within certain calculations and experimental contexts, yet they are no longer fundamental. Our language lags behind our understanding, clinging to metaphors inherited from centuries when intuition was our primary guide. This pragmatic ontology, the idea that concepts like particle are instruments rather than absolute truths, forces a reconsideration of what we mean by reality itself. The word particle does not dictate how nature behaves. Nature behaves according to fields, probabilities, and relational structures. Particle is a convenient fiction, a label applied to patterns that emerge when certain criteria are met. Energy is transferred in discrete amounts, a detector registers an event, or an excitation interacts measurably. These phenomena are real. The word we attach to them is contingent. The linguistic critique also illuminates the persistence of misconceptions in popular science. Textbooks, lectures, and media often portray electrons as tiny balls orbiting a nucleus, photons as bullets of light. These images are seductive precisely because they align with our evolved intuition for solid, tangible objects. Yet at the frontiers of physics, these images break down. Particles, as discrete entities with clear boundaries, vanish under scrutiny. They are no longer the bedrock of reality. They are convenient approximations, linguistic scaffolds for an emergent, complex world. Moreover, the critique extends to the interpretation of experiments. When we detect a photon in a scintillator or an electron in a cloud chamber, we speak of particles because it aligns with our human expectation of individuality and locality. Yet these events are better understood as localized excitations within a continuous field, patterns in a web of quantum probabilities, or manifestations of entanglement correlations. The particle label is imposed after the fact. It does not exist before interaction. Language, in this sense, is a lens, not a mirror. This realization challenges the very way we approach scientific explanation. It asks us to recognize that our conceptual categories, objects, particles, trajectories, may shape the questions we ask as much as the answers we receive. To advance understanding, we must adopt a vocabulary faithful to the ontology implied by quantum theory. Particle may remain useful in pragmatic contexts, but it must not mislead us into imagining a classical world that no longer exists. In essence, the universe resists the constraints of our language. Particles are not fundamental. They are linguistic artifacts that approximate, predict, and simplify complex emergent behavior. By acknowledging this, we begin to see reality more clearly, not as a collection of tiny things moving through space, but as a dynamic, relational, and continuous structure where excitations, correlations, probabilities, and fields are the true constituents of existence. The philosophical lesson is humbling. Words shape thought. By clinging to the term particle, we risk imagining a universe that conforms to human intuition rather than the evidence of observation and theory. By shedding this linguistic habit, we gain a clearer view of the quantum world, a world in which processes, relations, and emergent phenomena replace classical solidity, where the entities we name are ephemeral, context-dependent, and fundamentally contingent upon the structures we use to describe them. In asking whether particles are real, we are also asking whether our language is real, or whether it merely gestures at a deeper, subtler reality that refuses to be pinned down. And in this subtlety lies the next frontier of understanding. The recognition that the foundations of the universe may lie not in objects, not in things we can name, but in the patterns, relationships, and processes that underlie every observation, every interaction, and every event we call reality. Despite the dazzling precision and predictive power of quantum mechanics and quantum field theory, physicists themselves remain deeply divided over what, if anything, is really happening at the most fundamental level. The equations work, the experiments confirm them. Electrons scatter, photons interfere, particles appear and disappear, entangle and tunnel. Yet ask a physicist whether these particles, waves, or fields are truly real, and the answers diverge. There is no consensus. And this lack of agreement is not merely academic, it is profoundly instructive. Recent surveys, including a 2025 poll published in Scientific American, reveal the diversity of opinion. Among professional physicists, approximately 36% affirm that quantum entities like electrons and photons are real in a classical sense. Around 47% treat them pragmatically, viewing the wave function or particle concept as a tool for calculation rather than a description of objective reality. The remainder hold more exotic positions. Many worlds' adherents imagine reality as a branching universal wave function, while others entertain relational or process-based ontologies where particles are secondary to the structure of interactions. These numbers suggest that even at the cutting edge, certainty about what exists is elusive. Why does this matter? Because it underscores a vital principle. Physics advances not because we know the true ontology of the universe, but because we can predict phenomena and manipulate them with astonishing accuracy. Quantum theory does not need agreement about what is real to work. It produces technological miracles, semiconductors, lasers, magnetic resonance imaging, quantum computers. Reality's deepest layers may be mysterious, but mastery over patterns and correlations is sufficient for progress. The divergence in physicists' beliefs also illustrates a philosophical divide: instrumentalism versus realism. Instrumentalists argue that theories are tools, mathematical frameworks to predict observations. Whether the entities they describe exist independently is secondary. Realists, in contrast, insist that theories should reflect the true structure of reality. In quantum physics, instrumentalists often have the upper hand simply because reality defies classical intuition. The Copenhagen interpretation, for example, treats the wave function as a calculational device, not a description of an underlying object. Many worlds attempt realism, but at the cost of an infinitely branching universe. Path integrals and field theory often sidestep the question altogether, focusing on processes and excitations rather than independent objects. This plurality of perspectives demands humility. Even the most confident predictions are compatible with radically different pictures of the underlying reality. A physicist can compute the energy levels of hydrogen, the scattering cross-section of electrons, or the probability of tunneling events without committing to a single ontological interpretation. Nature works. Our understanding, however sophisticated, remains provisional. The epistemic limits revealed here are not flaws, they are features of the quantum enterprise. Physics, unlike classical mechanics, does not provide a straightforward map of the world as it is. Instead, it offers a web of correlations, rules, and patterns that reliably describe what happens. The interpretation of those patterns, whether particles are real, whether collapse occurs, or whether the universe branches endlessly, is secondary to predictive accuracy. Yet these debates illuminate the conceptual depths of quantum theory, reminding us that certainty is elusive even in a domain of remarkable precision. Surveys and commentaries, such as those in Nature Physics and Physics Today, highlight that disagreement is healthy and perhaps inevitable. As physicist and philosopher David Albert notes, the richness of quantum theory allows multiple internally consistent ontologies. Each framework, Copenhagen, many worlds, relational quantum mechanics, or quantum field ontology, captures aspects of reality, yet none can claim absolute supremacy. Our models succeed not by matching reality perfectly, but by providing coherent, falsifiable, and extraordinarily precise descriptions of phenomena. This recognition shapes the culture of modern physics. Researchers operate with pragmatic humility. They construct theories, perform experiments, and refine predictions, while accepting that the true nature of particles, waves, or fields may forever elude final description. Quantum theory works exquisitely well even when the question, what exists, is deferred, sidestepped, or answered differently by each practitioner. The philosophical implications are profound. It is a universe where certainty about existence is not guaranteed, where the foundations of matter are not agreed upon, and where objects, particles, and even fields are subject to interpretation. Yet the lack of consensus does not hinder progress, it fuels inquiry. The search for deeper understanding continues, constrained only by the rigor of experiment and the consistency of mathematics. Scientific humility, therefore, is not an admission of weakness, but a recognition of the universe's depth. The diversity of opinion among physicists is a testament to the subtlety and complexity of the quantum world. We are observers in a realm where predictive power is achievable, yet ultimate ontology remains elusive. The limits of what we can know become as compelling as what we can measure. By confronting this uncertainty, we are forced to rethink the relationship between knowledge, observation, and reality itself. Classical confidence in particles as tangible, localized objects is replaced by an acknowledgement that reality may be relational, emergent, or fundamentally probabilistic. The physicist's task is no longer to map things directly, but to understand structures, correlations, and processes. In the end, Part 14 presents a sobering yet exhilarating lesson. The universe does not yield its secrets in tidy, object-based parcels. Even at the highest levels of expertise, what exists at the quantum level is not a settled matter. The question, are particles real, does not have a single universally accepted answer. And perhaps it is precisely this epistemic openness, this willingness to live with uncertainty, that allows physics to advance, revealing ever more astonishing phenomena without demanding that nature fit neatly into our preconceptions. In acknowledging the plurality of belief among physicists, we confront a profound truth. Reality, at its deepest level, may be richer, stranger, and less tangible than the categories we have long relied upon. Particles, waves, fields, entanglement, paths. These are tools, patterns, and concepts. The underlying universe may elude definitive labeling entirely, and yet, despite this profound uncertainty, physics thrives. Its success is measured not by consensus about ontology, but by its unmatched ability to describe, predict, and manipulate the extraordinary tapestry of phenomena that quantum theory reveals. If particles are not fundamental, if the solidity of matter is an emergent illusion, then what, if anything, underlies the universe? Modern physics and philosophy suggest a radical answer. Reality may not be built from things at all. Instead, it may consist of information, relations, and processes, a web of interactions from which the phenomena we call particles, objects, and matter emerge. John Wheeler famously proposed it from bit, the idea that every physical quantity derives from yes or no questions, from discrete units of information. In this view, the universe is a vast computation where events and correlations form the substrate, and what we perceive as material reality is simply the outcome of underlying informational processes. Carlo Rovelli in Helgoland echoes this, arguing that quantum mechanics is a theory of relations. Properties exist only in interactions, not as intrinsic qualities of isolated objects. Reality, he suggests, is a network of relational structures, continuously evolving, with apparent things arising as emergent patterns. Process philosophy, too, offers insight. Instead of building the universe from enduring substances, it emphasizes becoming overbeing. Events, interactions, and patterns take precedence over fixed entities. Particles, fields, and even space-time may be understood as emergent features of deeper processes, manifestations of underlying dynamics rather than primary constituents. This vision transforms the way we think. No longer do we imagine the universe as a collection of independent objects moving through empty space. Instead, we see a dynamic tapestry of correlations, information, and relational processes. The universe is not made of stuff, but of structure, interaction, and computation. Particles were useful stories, approximations, shadows of a richer reality. We are left with a profound, humbling insight. Reality is not composed of things to be grasped, but patterns to be perceived. To understand the universe is not to catalogue its objects, but to discern the intricate web of relations and processes from which all phenomena emerge. In embracing this, our conception of existence itself evolves, from thinking in objects to thinking in patterns, from solidity to interconnection, from certainty to wonder. Thank you for joining us on this extraordinary journey through the universe on frontiers of infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.